Solving a polynomial equation is about the same as finding the zeros of a polynomial function. The notation looks a little bit different, but that's basically what you do. And so for the examples on this first page, a lot of polynomial equations, we actually already know how to do them. We already know how to solve them. So for something like this one, there's an x at least in every term, and to go a little bit further, there's at least an x cubed in every term, so we could factor that out. So if we factor out x cubed, we'd be left with x squared minus x minus 6, and then this also factors into x minus 3 times x plus 2. And then really we're just using the zero product property here, and we're saying, well, if x cubed is 0, then x would have to be 0. If x minus 3 is 0, then x is 3. If x plus 2 is 0, then x is negative 2. And that solves it. And that's really not using anything new. Example 2 and example 3 don't really use anything new either. With example 2, the main thing is you got to get a 0 on one side. So subtract 10x squared from both sides, you end up here, 3x cubed minus 10x squared plus 3x equals 0. There is a common factor in the three terms on the left, which is x, so we can factor that out. And then we're left with a product of x and 3x squared minus 10x plus 3. But 3x squared minus 10x plus 3 factors into 3x minus 1 and x minus 3. And then using the zero product property, either x is 0, x is 1/3, or x is 3. The last one on this page, example number 3, this is one that you could do by grouping. So I grouped the first two terms and the last two terms on the left side. In the first two, you could factor out an x squared, and you're left with 5x plus 1. And then in the second grouping, to be left with a 5x plus 1, you could factor out a negative 2. So there's negative 2 times 5x plus 1. And then you can rewrite that as x squared minus 2 times 5x plus 1. And then the zero product property again, either x squared minus 2 equals 0 or 5x plus 1 equals 0. If x squared minus 2 equals 0, then x squared is equal to 2, so x is equal to either positive or negative radical 2. And then if 5x plus 1 equals 0, then x would have to be equal to negative 1/5. On page 2, we have this idea up toward the top of equations that are quadratic in form. So ones that are quadratic in form, quadratic equations are quadratic in form, but you would just handle a quadratic equation the way that we've been doing it. So what are ones that are quadratic in form, but they aren't actually quadratic equations? They tend to look like this, where you have two terms that have x's in them, and when you look at the two exponents, one is twice the other. So like how here there's an x to the 6th, and here there's an x cubed. The way that that's quadratic in form is that you can make a substitution that results in a quadratic equation when this happens, when one of those exponents is twice the other. So watch what happens here. If you say, well, what if u is x cubed? Then you end up here, where with the 3u, right there, the u just goes straight in for x cubed. But then if u is x cubed, x to the 6th is x cubed squared. So then that becomes u squared. So 2u squared plus 3u plus 1 equals 0. You look at this and you go, oh, that looks like a quadratic equation if u was the independent variable. And then we could solve for u, like the way that you would normally solve a quadratic equation. That's true. And that's what you do with it. And then at the very end, if you want to solve for x, you just have to sub back in that x cubed is equal to u, and you can solve for x from there. So in this example, this is quadratic in form because 4 is what you get when you multiply 2 by 2. So I said, well, let u equal x squared. Then what we're left with is u squared minus 13u plus 36 equals 0. That factors into u minus 9 and u minus 4. And then if you use the zero product property, either u minus 9 is 0, so u is equal to 9, or u minus 4 is 0, so u is equal to 4. But we don't want the answer in terms of u. We want this to be solved for x. So then we have to back substitute and say, well, when we subbed in, we said u is x squared. So if u is equal to 9, then that means x squared is equal to 9. And if u is equal to 4, that means x squared is equal to 4. But then going back over here on the left, if x squared is 9, then x is plus or minus 3. Then on the right, if x squared is 4, then x is plus or minus 2. So you get 4 solutions here. Positive 3, negative 3, positive 2, and negative 2. And the other example on this page is the same kind of idea. First, you want to get it where there's a 0 on one side, though. So you subtract 11x squared from both sides, you end up here. But this is another one that's quadratic in form because 4 is 2 times 2. So it's the same substitution. You let u equal x squared. So then you'd have u squared minus 11u plus 10 equals 0. That factors into u minus 10 and u minus 1. So either u is equal to 10 or u is equal to 1. Back substitute. So you'd say either x squared equals 10 or x squared equals 1. But then that means that either x is equal to plus or minus radical 10 or x is equal to plus or minus 1. And so the answer ultimately doesn't look too different from the answer in number 4. These you could also do with larger exponents. So like in that one up toward the top, if I scroll back up for a second, up here, there it is, with the x to the 6th and x cubed, you could do that, or if you had like an x to the 8th and an x to the 4th, or an x to the 10th and an x to the 5th. Although going above a quartic, you do get things that have the potential to get a little wild. So like this is solvable, but you can get things that are a little bit crazy when you get those big exponents. But you can still do them. But we're going to mostly focus on when you have a quartic that looks like that. So like what example number 4 and example number 5 are like. For the examples on the third page, these are ones where you have inequalities to deal with. So we're supposed to solve p of x equals 0, p of x is less than 0, and p of x is greater than 0. The way that these tend to work in the homework is that they give you the regular polynomial multiplied all the way out with the exponents in decreasing order, and they also give you the factored version. The factored version makes the first part easy. So p of x equals 0, well then that's pretty easy to find the roots when it's already factored. Right? You go, well, 3, negative 2, negative 5. So that's it, right? P of x equals 0 when x equals 3, x equals negative 2, or x equals negative 5. So then in set notation, there's the answer, right? 3, negative 2, negative 5. How do you do the rest of it where you have the inequalities? Well, it kind of springboards off of where you know the zeros or the roots are going to be. And you can do the two inequalities at once. So how I've got this number line here, the minuses and pluses actually go in later. What I would do first is I would draw the number line and put the zeros in there. So the negative 5, negative 2, and 3. And then to see where you have positive and negative values for p of x, you just have to check these 4 intervals. So that's what I'm doing here. I'm just picking numbers that fit into those intervals. What I would say first of all is if you can use 0 here, do it. So 0 is between negative 2 and 3 because that's going to be the easiest possible computation, right? That's just getting the y-intercept. So that's just the number at the end, right? So p of 0 is just negative 30. You go, okay, well, that's below 0. That's negative. So between negative 2 and 3, got to be negative. So that's how I've got that minus right here. Then for bigger than 3, I figured the simplest x value that I could pick would be 4. So I evaluated p when x is equal to 4, ultimately get 54. That's a positive number, so I got a plus out here. Then between negative 2 and negative 5, I picked negative 3. I guess you could also pick negative 4. It'd be about the same level of difficulty. But p of negative 3 is 12. That's positive, so I get a plus in there between the negative 5 and the negative 2. And then for something less than negative 5, I picked negative 6. So then p of negative 6, negative 36, that's a negative number. So negative, positive, and then the solutions for p of x less than 0, it's where the two minuses are. So negative infinity to negative 5, and then negative 2 to 3. That's what I've got down here, the union of those two intervals. And they should be open intervals. You don't want to include the endpoints because at the endpoints, p of x equals 0. Then for p of x greater than 0, it's where the two pluses are. So up here between negative 5 and negative 2. And then here above positive 3. So there's the interval from negative 5 to negative 2. There's 3 to infinity, and the union of those would be that answer. Now, I should also point out you could do less work here if you want to. If you're resourceful about when you end up with the function crossing or touching the x-axis, you could say, wait a minute. If we go up here, all 3 of these have multiplicity 1. So it's got to switch signs every single time. So if all you got was the y-intercept and you knew this was negative, it's got to switch signs here and be positive. It's got to switch signs over here and be positive, then switch signs again to go back to negative. So really you could just figure out the y-intercept and then manufacture the rest of this without actually doing this computation. If you're comfortable doing that, you can do it. I think that's resourceful, and if that's a thing that you think of right away, certainly you can use it. It's correct. There's nothing wrong with it. But if you'd rather do it with evaluating at every interval, just to have like a nice consistent system that you use every time, that's fine too. Whatever works, whatever feels like it's easier, do it that way. The other example that's here, we've got the polynomial written out where it's multiplied out all the way, or where it's factored. The factored one is going to be a little bit more helpful because we can look at this thing and go, well, where's p of x equals 0? When x equals 0, x equals 4, x equals negative 2. So there's that, and then there it is written in set notation. But then to get the two inequalities, that'll break up the number line. So you'd make the number line and say, okay, we need a negative 2, we need a 0, we need a 4, we need to get those zeros or those roots in there. Then we just have to check the intervals. Can't use the y-intercept this time because the y-intercept here is 0, so it doesn't help us. So I just went left to right. I said for less than negative 2, I'm going to pick negative 3. And p of negative 3 eventually works out to be negative 63. So okay, that's negative. Then p of negative 1, if you sub in a negative 1, you get 5. That's positive. P of 1, you get 9. That's positive. And then p of 5, you get negative 175, so that's negative. All right, so our two solutions for where p of x is less than 0, it's where the minuses are, so it's on the ends, right? It's down here less than negative 2. It's up here greater than positive 4, so it should be this down here, the interval from negative infinity to negative 2, union with the interval from 4 to infinity. You got to be careful with the other one because you're going to look at where the pluses are. That's correct, right? So you look up here and you go, there's a plus, there's a plus. The temptation is to say it's the interval from negative 2 to 4. That doesn't quite work because at 0, p of 0 is 0. It's not positive. So you still have to take these individually and say it's the interval from negative 2 to 0 union with the interval from 0 to 4. And again, just like with the other example, you don't want to include the endpoints because at the endpoints of these intervals, p of x is 0. It's not positive, it's not negative, so you don't want to include those. But that's a thing to kind of be careful of here, I think, where you have the two pluses next to each other, or if you get two minuses next to each other, you still have to have those individual intervals there because there is going to be that number in between the intervals where you actually get 0, not a positive in this case. And once again, like with the last one, where if all we had was the y-intercept, you could do the rest of it using multiplicity. You can do the same thing here. 0 has multiplicity 2, but then 4 and negative 2 are multiplicity 1. So let's say if all I did was I got p of negative 3 equals negative 63. So I knew that would have to be negative. 2, or negative 2 rather, has multiplicity 1, so sign's got to switch, right? Because the graph has to cross the axis, so that's got to be a plus. But 0 has multiplicity 2, so it's going to touch but not cross. So if it's a plus here, it's got to be a plus there. And then 4 has multiplicity 1, so it's got to cross again, so the sign's going to change, so it goes plus to minus. So you could manufacture all those other signs that way with just evaluating the function at one point, kind of like we did in example number 6. So again, if you want to use multiplicity, you can, but if you want to just do it this way, where you evaluate the function in every individual interval, you can do it that way too. The complex nth roots theorem is at the top of page 4, where if you have an equation that looks like this, where n is some power and then k is some number, then that equation is going to have exactly n complex roots. So example 8 should have exactly 2. Example 9 should have exactly 2. Example 10, if I scroll down for a second, should have exactly 3 because there's an x cubed. Okay, well 8 and 9 are pretty quick because here you could just use the square root property and say, well, if x squared is negative 36, then x must be plus or minus the square root of negative 36. So then negative 36, well, that square root is going to be 6i, right? Because you could factor out the square root of negative 1, that's I, square root of 36 is 6. So plus or minus 6i, that's two complex roots. That's what we were supposed to get because we have an x squared here. What about with x squared equals negative 28? Well, we can kind of do the same thing. We do the square root property, factor out the I, and then you could factor out a 4 out of this, right? This would be the square root of 4 times the square root of 7. The square root of 4 is 2. So x is plus or minus 2 radical 7i, 2 different roots. That's what we're supposed to get because we got the x squared. All right, well, how about example 10? This one's a little more drawn out. X cubed equals 64, or x cubed minus 64 equals 0. Knowing that 4 cubed equals 64, that's one solution, right? So x equals 4 is one of them. So that's why I've got that underlined red and I've got the 1 up there. So that's the first one. And then the best thing to do, I think, is to rewrite x cubed minus 64 as a product of x minus 4 with something else, and then just factor the something else to get the 2 other roots. So I did synthetic division here, and then what we end up with is that x cubed minus 64 is x minus 4 times x squared plus 4x plus 16. And then we just have to figure out the roots or the zeros of x squared plus 4x plus 16. And I use the quadratic formula to do it, although I suppose you could also complete the square. So subbing into the quadratic formula, simplifying, eventually you end up with a negative radical 48, and then, or the square root of negative 48 rather. And then you could factor out the I, and then 48 is 16 times 3, so you could rewrite the square root of 48 as 4 times the square root of 3, and you end up here when you simplify it down as far as we can get. And those are the second and third solutions because of the plus or minus, right? That'll give you 2 different numbers. So the answer, it's these 3. You have 4, you have negative 2 plus 2 radical 3i, and you have negative 2 minus 2 radical 3i. Example number 11 is about the same thing as example number 10. It's another cubic, and it's another one where you can get one of them right away, where you can say, well, negative 5 cubed would give me negative 125. So one solution has to be negative 5, right? So x equals negative 5, that's the first one. And then I rewrote x cubed equals negative 125 as x cubed plus 125 equals 0, because then I used synthetic division here to rewrite x cubed plus 125. It'll be x plus 5 times x squared minus 5x plus 25. And then we just have to figure out what the roots or zeros of x squared minus 5x plus 25 are. So I use the quadratic formula again. So sub in and then simplifying. Eventually you get 5 plus or minus 5 radical 3i over 2. And those are the other 2 complex solutions, the second and the third, because of the plus minus. That'll give you 2 different numbers. So the answer, negative 5 halves plus 5 radical 3 over 2i, and 5 halves minus 5 radical 3 over 2i. Then example number 12. This one has a higher degree. It's got an x to the 4th in it. But this actually isn't too bad because 3 to the 4th is 81, right? So this shouldn't work out to be too ugly. So if I rewrite this and say, well, then x to the 4th minus 81 equals 0, this is actually a difference of squares because x to the 4th is x squared squared, and 81 is 9 squared. So we could factor it like it's a difference of squares and say, well, then this is x squared plus 9 times x squared minus 9. And then using the zero product property, either x squared plus 9 equals 0 or x squared minus 9 equals 0. So then if x squared plus 9 equals 0, then x squared is equal to negative 9. And then the square root property, x is plus or minus the square root of negative 9, which would mean that x is plus or minus 3i. So there are 2 solutions. And then if x squared minus 9 equals 0, x squared equals 9, so x is plus or minus 3. There are 2 more, right? Number 3 and number 4, and that's how many we're supposed to get because the degree here is 4. We do get 4 solutions. So our answer, 3, negative 3, 3i, and negative 3i. So we do get 4 solutions there.